Alright, so now we're going to talk about some common oxidation and reduction reactions. So these are all things in the next couple of slides that you're going to have to memorize. For example, here are three very, very common reductions that happen in acidic solutions, and only in acidic solutions. So nitrate, if you think of nitrogen, in this case, it's got a +5, and it's going down to a +3. So nitrogen, which is normally a -3, if you look at it on the periodic table, if it forms an anion, it wants to be in a fairly low oxidation state. So if it's sitting at something like +5, it's not going to be happy there. It really, really wants to gain electrons. And so if you're given a reaction that involves nitrate in an acidic solution, you should know then that it turns into NO. Permanganate, MnNO4, it's going to turn into Mn2+, which is the more happy form of manganese. Dichromate turns into Cr3+. So these are just, if you're asked to predict what the products are, you need to recognize what these three are and know what they turn into. Another common one would have sulfite, turn it into sulfate. And hydrogen peroxide generates oxygen gas, and it also forms, if you're wondering about balancing, H2O as well. And if you're keeping score, you'd put a 2 there and a 2 there. Now here's some examples of things that really, really want to lose electrons. So if we look at C2O4, the carbon has an oxidation state of +3. Carbon, which is a group 4A element, really wants to have an oxidation state of +4. And so it's going to lose a couple of electrons and turn into CO2. And so then this one you need to remember then is oxalate, C2O4, 2-. You should know that ion already. When it oxidizes, it turns into carbon dioxide. Some nonmetals then that are ions, for example chloride, can bond with themselves or with like elements to generate something that has a much lower oxidation state. So like Cl- bonds with itself to form Cl2, which is going to go from a -1 oxidation state to a 0 oxidation state. Ooh, so here's a tricky one then. What if you have both a metal and a nonmetal that can be oxidized? So for example, we've got tin, which is Sn2+, in this case, and then Cl-. So I already showed you guys how Cl-, and we've got two of them, they can lose their electrons to turn into Cl2, or tin can lose 2 electrons to enter the oxidation state of 4+. The metal will be oxidized. Metal wins out. It's going to lose its 2 electrons, turn into a happier oxidation state of +4. Alright, let's take a look at some examples and why it is that you need to memorize those. So here's an example of a problem you would see. Tin 2-chloride is mixed with a solution of potassium permanganate. So first off, let's go ahead and choose who our reactants are going to be. So we've got 4 different guys. We've got tin, we've got chloride, we have potassium, and then we have permanganate. So let's talk about the potassium permanganate first. Which one of those is likely to undergo a redox reaction in an acidic solution? Well, if you have yours memorized, you're going to recognize that potassium, first off, is a group 1 metal. It's always soluble, so more than likely it's going to be a spectator. So we can go ahead and cross that off. Permanganate, on the other hand, is one of those things that is easily reduced inside of an acidic solution. And here we go, acidic solution, permanganate. Go ahead and write that guy down then. Now you need something to react with. Question is it going to be tin 2 or is it going to be chloride that is going to be oxidized? We just saw on the previous slide how it's always the metal that wins out. So in this case, that means that chloride is probably going to be a spectator. So it's going to be manganese plus tin 2. Now it's time to choose our products. So permanganate. We've memorized now what does permanganate turn into in an acidic solution. It turns into manganese 2+. So that means it's going to form Mn2+. And then tin, it's 2+ charge right there. If it is being oxidized here, we know that permanganate is reduced, which means that tin has to be oxidized, so it's not going to gain any electrons. Manganese is doing that. So that means it'll turn into its other oxidation state, which is 4+. This is why you need to know your oxidation states of metals. Alright, we're done, right? Oh, no we're not. Let's balance this thing. We've got oxygens on this side, but none on that side. This is taking place in an acidic solution. What do you think we got to do? Yeah, we got to balance with the half reaction method. Alright, so starting with the redox half of the half reaction, let's balance who is reduced, and that would be the permanganate. Okay, so there's step 1. Step number 2, we need to balance the manganese. Those are already balanced, so we can go to step number 3, balance the waters, or balance the oxygens using water. And so we've got 4 on the reactant side, which means we're going to need 4 waters on the product side. Brings us to step number 4, balance the hydrogens. Going to add 8 H pluses to this side to balance out those hydrogens. Now we need to balance charges. So on our reactant side, we have 8 plus and minus, which means we have an overall charge of 7 plus. And on our product side, we have 2 plus and neutral, which means an overall charge of 2 plus. So to get those two to equal each other, we'd have to add 5 electrons to the reactant side. And that will make our charge on this side a grand total of 5 plus to match up, 2 plus to equal up with our product side. Now let's go ahead and do the oxidation half of the reaction, which would be the 10 turning from 2 plus to 4 plus. Once again, this one's pretty easy, so we can just go ahead and squirt on through to step number 5, balancing the charges. And we would have to add 2 electrons to this side to give us an overall charge of 2 plus on both sides. And here they are written out nice and neat. So in order to balance then the electrons, we'd have to multiply this top one by 2 and this bottom one by 5. That way we show 10 electrons being lost, 10 electrons being gained. And we do that, we cancel out the electrons, sum those two reactions together, and here we have our balanced redox reaction for tin 2 chloride and potassium permanganate. Now this would be your net ionic reaction here. We've left out potassium, we've left out the chloride, because they're not going to change on either side. We have those acids in there, we have the waters in there, because they are going to be changing states. The H pluses are turning into the waters, the oxygens from there are combining with it to make new H2Os inside of the solution. If you're worried that you're going to use the half reaction method in the wrong place, so in a redox reaction where you don't have to use it, it doesn't matter, don't worry. You can use it for any reaction you want. It'll always work, because if there's no oxygen or hydrogen in it, then you just skip the first couple of steps and you go to the last one and it comes out all right anyway. So don't be worried about overzealously using the half reaction method. Go ahead and use it all the time. If it helps you, if it works for you, great, do it. It's like my grandma used to always say, it's better to use the half reaction method when you don't need it than to not use it when you do need it. Here's an example of a problem that showed up on the 2009 free response portion of the actual AP test, where knowing how to write the half reaction method actually came in handy for a non-acidic solution question. So in this case, they were just asked to write the oxidation half reaction for the decomposition of hydrogen peroxide. And so what this means is we have H2O2, and this is aqueous or liquid, so we can't break it apart any farther. And it is turning into, for the half reaction, O2, where it's going from an oxidation state of -2 to 0. We wouldn't show the hydrogen peroxide turning into water because the oxygen in water is still -2, so it's not showing it changing. And then in this case, to balance that guy, hydrogen or oxygen's already done. To do the hydrogens, we'd have to add 2 H pluses, and then to balance the electrons, we would have to add 2 electrons to this side as well. So then this is where knowing that half reaction method came in handy, because otherwise you might not have put those H pluses in there. And you could have spun around in circles forever trying to figure out how to balance those hydrogens. And so this would have been the proper answer and gotten full credit on the 2009 free response test. All right, we've talked a lot about acidic solutions. Let's go back and talk about basic solutions now. So basic solutions are solutions that have a high concentration of hydroxide ions. Once again, here's a couple guys you're just going to have to memorize on things that change in basic solutions. So permanganate, for example, when it's in a basic solution, is going to change into MnO2. This is different because in an acidic solution, permanganate turned into Mn2+, but in a basic solution, it turns into manganese dioxide. Here's an example. Keyword, it says basic solutions. That should be a hint. Basic solution, magnesium sulfite and potassium permanganate. Alright, let's pick our players for this who are going to be our reactants. Potassium, it's always soluble. Let's cross that guy out. Not going to be in the reaction. and magnesium sulfite. Well, magnesium is soluble with everything here, so it's not going to react with anything we see. Sulfite, though, does tend to lose electrons, and when it does, it turns into sulfate. So magnesium is out. So here we go, manganese and sulfite. Let's talk about what they're going to turn into. So it's a basic solution. Manganate, permanganate, what does it turn into? It turns into MnO2. And sulfite, when it is oxidized, turns into sulfate, SO4, 2-. Now it's time to balance. We have 4 oxygens. We've got 3, so a total of 7. We've got 2 and 4, that makes 6. Can we do this with just regular numbers? No, it turns out we can't. We have to do the half reaction method. So we talked about half reaction method in acidic solutions, and it's not that much different for a basic solution. There's just one more step that's added to the very end, and it's a pretty simple step. So let's just go through the normal steps. This will be good practice using this method. So first thing, let's write a reduction half reaction. And hey, why don't you go ahead and pause the video and see if you can go through and do this one. Get all the way to the end, get your final written out reaction, and then check it with mine. The last step, the one you don't know yet, doesn't really matter. When we get to the end, we'll talk about that one. Alright, I'm going to cruise through this pretty quick so you can check your answers. Alright, so we would need ourselves 2 waters to balance the oxygens on both sides, and then we would need 4 H pluses to balance out the hydrogens that we added with the waters. And then to balance our charges, you would need an additional 3 electrons on the reactant side. And now on to our oxidation half. In this case, we're doing sulfite to sulfate. This one was different than the others because we had to use water and H plus to balance it as well. So we added 1 water to the reactant side and then 2 H pluses to the product side. And then for electrons, we'd have to add 2 electrons onto our product side to balance those charges. And to get them equal, we multiply one by 2, the other one by 3. That'd give us 6 electrons being transferred in between. Finally, on to the combining phase. And hey, this is actually good because we can see an example where we have more than just the electrons on both sides of the reaction. So if we look here, we have 8 H pluses on one side and then 6 H pluses on the other. So we can cancel part of those out then. We can take away 6 hydroxides or 6 H pluses from both sides of the reaction. So if we subtract 6 from this side, that's going to cancel that guy out. And if we subtract 6 from this side, it's going to leave 2. We can do the same things with water. We could take away 3 from the reactant side and 3 from the products, leaving us with 1 water on the product side. Now it's just a matter of copying everything down, and that leaves us with this grand total of a reaction. So we've canceled out some of those H pluses and some of those waters on either side to make a nice clean reaction. However, this is where the new step comes in. So remember, this is a basic solution, and basic solutions don't have H pluses in them. They have hydroxides instead. So our final step then, we would need to get rid of those H pluses by adding hydroxides. So for every H plus that's in the reaction, you have to add a hydroxide to both sides of the equation. So in other words, there's 2 H pluses right there, so we'd have to add 2 hydroxides to this side of the reaction, and those guys are going to combine to form 2 waters. Now, if we added 2 hydroxides to the left side of the equation, we have to add them to the right side as well. And so we would add 2 hydroxides to this side as well. And there's nothing over there for them to combine with, so those are just extra hydroxides that are from the basic solution itself. So here it is written again, and there it is completely combined into one complete and awesome looking reaction. And the last thing to talk about real quick is a redox titration. So redox titration is just something you use to determine an unknown concentration of a species that can be oxidized in a solution. So you have a solution with a known concentration, and you have a solution with an unknown concentration, and you add them together until they reach what's called the equivalence point. And the equivalence point occurs when you have an equal number of moles of species that are being oxidized and species being reduced that are combined. And so usually you recognize this because a color change happens, and so that means you've reached the end point. We did titrations with acids and bases. It's the same general idea. So you get it to where the two things are equal, you figure out your unknown concentration. So here's an example. Potassium permanganate is actually a bright purple color. and when it combines with iron 2 plus, it forms manganese, Mn2 plus, and iron 3 plus. So the difference between permanganate and manganese 2 plus is that this is colorless. So if we drip this into a solution of iron 2 plus, it's going to use up that permanganate, turn it into Mn2 plus, which is colorless, so clear. So it would disappear when it touched that solution. So we put that in there. As we drip it in there, if we have an unknown solution or unknown concentration of Fe2 plus in there, as we're adding them, we can see how much permanganate it takes to use up all of that right there. Once we've added enough permanganate, it's going to start turning purple down here, which means we've used up all of the 2 pluses. We can then go back and calculate, all right, if I added this much permanganate, there must have been that much iron 2 plus in the original solution. So that's a crash course in redox titrations. We're going to do one in class. We'll talk more about it and what's going on. So hopefully it'll give you a better understanding of exactly what happens.